All right, today's lesson is on properties of exponents. So to really understand our properties of exponents, we're going to go through an example with some numbers and look at what's called expanded form for each. And that will help us derive and hopefully better understand each property. Okay, so you may need to pause the video to write down our properties, the example, in expanded form before each part, and then we'll explain them afterwards. So this would be a good time to pause and write down the first part. Okay, so looking at our example, we have m to the third power times m to the fourth power. And the property that we're looking at is if we're multiplying two things that have the same base. Okay, so the bases have to match here. So for instance, our m and m. And remembering what these exponents mean, right? Exponents are the way we write repeated multiplication. So m to the third means m times m times m, and m to the fourth means m times itself 4 times. And if we're just multiplying them together, I just used a big multiplication dot here, well really that just means now we have 7 m's all multiplied together. So we can think of how can I get to that value of 7 from the exponents in my example. And hopefully you can tell by looking at our numbers that we would add our two exponents, 3 plus 4, or m to the 7th power. So our property over here is if you're multiplying two things that have the same base, we can keep the base and add our exponents. Okay, here's our next property. In this one, we have something that already has a power being raised to another power. So we like to call this a power raised to a power. So for instance, if I have m squared being raised to the third power. There's our example. Okay, so in expanded form, think about what this means. That exponent on the outside means I have this quantity times itself 3 times. So we have our 3 parentheses times itself. And inside, each one of those has an m squared, which means m times m. So if we think about, again, these parentheses being next to each other just meaning more multiplication, we really end up with just 6 m's being multiplied together, m to the 6th power. So again, if we're looking at how can I get to that exponent of 6 back here from our two previous exponents? And of course we can tell when I have a power raised to a power, we multiply the exponents. So this becomes m to the 6th, right? In other words, we had 3 sets, 3 sets of 2 m's, right? And that's why we ended up multiplying there. So when I have a power raised to a power, we multiply. This becomes a to the m times n power. Okay, here's our next example. Again, make sure when I first reveal these that you stop and take time to write them down before we begin going over each. So in our new one, we're dividing two things that have the same base. Okay, so again, the bases have to match, but we're dividing things that have exponents. So for instance, m to the 5th divided by m to the 3rd. So again, we're going to write those out in expanded form, m to the 5th being m times itself 5 times, m to the 3rd, m times itself 3 times. Now, remember, the reason we're allowed to reduce fractions is we can cancel common factors, right? Technically, m divided by m turns into 1, right? Anything divided by itself is 1. So we can think of, we can end up canceling 3 sets of m's up here. These all essentially become 1s. So m times 1 times 1 times 1 just becomes m times m. We get m squared over 1, right? We can even think of these as becoming 1s in the bottom, not an exponent, but just a value of 1. So the placeholder in the bottom, if there's nothing remaining, we get to cancel everything out, would be a 1. And if there's just a 1 in the denominator, we don't need to write it as a fraction. So in this case, m squared is our answer. So I want to think about how can I get to that exponent based on what we started with. And hopefully we're able to tell, in this case, we end up subtracting the exponents. And in the order of the top minus the bottom. So that would give us m squared for our answer. So hopefully that makes sense. If I'm multiplying two things with the same base, we add the exponents. If I'm dividing two things with the same base, oops, this erased my answer over here. If we're dividing two things with the same base, we subtract the exponents. And it is in the order. Remember, when you subtract, order is important. So it is the top minus the bottom. Okay. Well, our next one is, what happens if I get a negative exponent? Okay, maybe that wouldn't be an obvious question here, but let's say I have that same fraction, but the reciprocal, right? The flipped upside down version. Now, m to the third is up top, m to the fifth is in the bottom, right? Obviously, this could be a case we can run to as well. We can cancel out three sets of m's. Again, these all become ones. And we end up this time with a 1 as a placeholder in the top of the fraction and m squared in the bottom. So if I followed our same pattern, right, we just had a rule that says if I subtract the top minus the bottom, we end up getting a negative exponent. 3 minus 5 is negative 2. Well, we're not supposed to leave negative exponents in an answer. It's said to be unsimplified. So if I look here, and I looked here, how can I make, and this is the correct answer, how can I make this so it doesn't have a negative exponent? And the answer is that if I thought of this as being a fraction, so just any value, right, we can put over 1, to make my exponent positive, we actually take this value, whatever has the negative exponent, and we change its place in the fraction. So that's actually going to move to the bottom and become a positive exponent. And because there's nothing left up top, we're just going to put a placeholder of 1. So 1 over m squared. So how we deal with negative exponents in math is I can think of this as being over 1. And we're going to move it to the denominator. So a to the positive m, but in the denominator. This also works for if you had a negative exponent in the bottom of a fraction, you would simply move it up and make that positive m to the third up top. Okay, here's our next one. And you may have learned this fact before. Anything to the 0 power. Okay, so we'll show you where that comes from, why that has to be true, why everything to the 0 power is this value. And we're going to continue by looking at fractions. So here's our example. What if I had m to the third over m to the third? Right, well, we would know here's our expanded form. That's just 3m's being multiplied together in top and bottom. And well, actually, everything cancels out. We end up getting 1 over 1, or 1. Similarly, if I thought about this, though, using this rule, right? If I'm dividing two things with the same base, we can subtract their exponents in the order of the top minus the bottom. So 3 minus 3, which gives me an exponent of 0. But looking over here, we know everything would cancel out in the top and bottom, or that anything divided by itself should equal 1. And that's where this property of exponents comes from. Anything to the 0 power will always equal 1. Okay, here's our next property. Now, notice this time the bases don't have to match. So this says if I have things held with multiplication, and that quantity is raised to another power. So something like this might have 5 times x squared, right? They're held with multiplication, and it's being raised to a power. So again, if we go to our expanded form here, you can think of this as this quantity, right? Our set of parentheses times itself 3 times. So we have our 3 sets of parentheses. And inside each, we have 5 times x squared, which means x times x. So I fully expanded that out here for this form. Well, if we think about what we would get here, I'm going to have 5 times 5 times 5. Remember, this is all multiplication. So as a sub-step, I could write that as 5 cubed. But I'm also going to have 1, 2, 3, 4, 5, 6 x's being multiplied. So x to the 6th. Now you could simplify 5 cubed. 5 times 5 times 5 ends up being 125. So you could simplify your answer all the way to this. But to get our property, we won't necessarily need to go that far. So more similarly, I want to look back at this part. How do we get to these exponents from what we had here? And you might notice that if I were to take this 3 and make 5 cubed and x squared cubed, if we raised both of them to that power, well, we would get the 5 cubed that we got over there, which ends up being 125. I'm just going to leave it as 5 cubed in this section because I'm going to run out of room. But here, right, we had a property for if I have a power raised to a power, we multiply the exponents. So 3 times 2 would be 6x to the 6th. So yes, we could calculate 5 cubed and write that as 125. But more importantly, this is helping me figure out that if I have multiplication inside my parentheses, we can distribute an exponent over that. So this m will get applied to both a and b. So we can write this as a to the m times b to the m. So you can distribute across multiplication. Okay, one thing to be careful of, you cannot distribute over addition or subtraction. So if you got this, you cannot distribute over addition or subtraction. If there's any adding or subtracting going on in that parentheses, you cannot distribute. So a common mistake, please be careful. You can if there's only multiplication, or as we'll see in our next property, if there's only division. Okay, here's our 7th and final property. And it makes sense that if we're allowed to distribute exponents over multiplication, that we'll probably be able to do the same if we're distributing over division only. So in this case, if I have x over 5 cubed, again, that means this set of parentheses times itself 3 times. And when you multiply fractions, it's the top times the top. So we get x times x times x, or x cubed. And at the bottom, 5 times 5 times 5, which is 5 cubed. And yes, once again, we could make that 125 as a final answer. But again, hopefully we can see here that this allows me to distribute this 3 to both the top and bottom. So we end up with x cubed over 5 cubed. Okay, so makes sense. Again, if we can distribute over multiplication, we will be able to distribute over division as well. So this m, we can distribute to the x and to the b. So again, you can distribute exponents over multiplication and division, but not addition or subtraction. There is no property for that. That one you would have to write some sort of expanded form for, like expand it out and perform the operations. Okay, so let's try some of these properties out. So in example 1, we're multiplying two things with the same base. So looking back at our properties here, if I'm multiplying two things with the same base, we can keep our base and add the exponents. So this would give us y to the 5 plus 7 power, or y to the 12th power. And that's it for number 1. Hopefully that part's pretty easy. For example 2, we have a couple things being multiplied and raised to a power. So let's check our properties. Down here, if I have things being multiplied and raised to a power, we can distribute that exponent to both. So here we can take our 4 and distribute it over multiplication. So we get 3 to the 4th times a to the 4th. So 3 to the 4th can be calculated. It's 3 times 3 times 3 times 3, which ends up being 81a to the 4th. Okay, example 3 has a lot of things going on over here, but don't let yourself get overwhelmed. Let's take these one at a time. The first thing I see is we have a power being raised to another power. So let's check our properties. If I have a power raised to a power, we can multiply our exponents. So this first part becomes m to the fourth power. Over here we have basically the same thing. Two exponents, power raised to a power, so we'll multiply those as well. That gives me m to the negative fourth. And these things are being multiplied together. So if we're multiplying two things with the same base, like we have here, very similar to the property we just used in example 1, we keep the base and add the exponents, which actually gives me m to the 0. And what was anything to the 0 equal to? 1. So that whole thing just ended up equaling 1. Okay, let's try example 4. Now I see we have a fraction. We've got some multiplying going on in the top and bottom, but we can first try to simplify the numeric part of our fraction, or the numbers. So 40 and 5 both have a divisor of 5. So if we divide top and bottom by 5, we get 8 and negative 1. Okay, x to the fourth over x squared. If I had a negative exponent, we'd want to deal with that first, but we don't. So I'm going to go back to, what do I do if I'm dividing two things that have the same base? So remember here, if we're dividing two things that have the same base, we subtract them in the order of the top minus the bottom. So I could do some side work here. X to the fourth minus x squared, so 4 minus 2 would give me x to the second. Okay, now if you use this subtraction method, your answer always goes in the top of the fraction. So x to the positive second goes up here. Okay, now if you wanted to, you could have also visualized the x to the fourth in expanded form and x to the squared in the bottom, and imagine canceling out two sets of x's, leaving you with 2 up top. Okay, that's my preferred method, but if you are welcome to use, of course, the property of subtraction. There are some times when that's better, but whatever answer you get always starts in the top of your fraction. Now here, if there's just a negative 1 in the bottom, it's almost not a reason to leave this as a fraction. So just like you can divide fractions, top and bottom, by a number, you can also multiply. So typically we don't want to leave a negative 1 in the bottom. So I'm going to multiply top and bottom by negative 1, which would give me 8x squared over negative 8x squared over positive 1, which doesn't need to be a fraction anymore. Okay, here's our last 4 examples to go over. So let's take a look at example 5. So first thing I see is we do have a fraction inside, so I might be able to simplify some things in there first, but I don't think there's much simplifying we can do. So we have this whole quantity being raised to the fourth. Well, I know that we are allowed to distribute over division, right, based on this property. We're also allowed to distribute over multiplication. So if there's a combination of those, we can distribute over all of them. So in this problem, because there is multiplication in the bottom and division, we're allowed to distribute our 4 as an exponent to everything. So the top is going to become 1 to the fourth power, and the bottom is going to become x to the third raised to the fourth. Now, I wouldn't usually write this step, but just for our notes I will, times y squared to the fourth. So remember, in each case for these, a power raised to a power, if you have a power raised to a power, we multiply our exponents. So 1 to the fourth power, 1 times itself 4 times, is just 1. And multiplying our exponents here, we get x to the 12th and y to the 8th. And here's our answer. Okay, example 6 is very similar to example 4. So if you want to pause the video and try it yourself, this would be a good time. Okay, so here I see we do have some things that we can simplify. We've got all multiplication in the top and all multiplication in the bottom. That's good. That will allow us to cancel common factors. So for the numbers, if we divide everything by 2, I'll get a negative 1, and 24 divided by 2 is 12. Okay, so then I look at my first variable c. I notice I don't have any negative exponents. That's good. So if I want to use when I have two of the same bases being divided, we have this property that says I can subtract my exponents in the order of the top minus the bottom, 3 minus 2. So 3 minus 2 is 1, and that would start again in the top of my fraction. Okay, I can repeat the same thing with d. Neither of them is negative. Even if they were, if you're using this subtraction method, you're still okay. So I get d to the fourth, and that also goes in the top. So for a negative one, I wouldn't usually need to write the number there, just a negative sign. C to the first is really just c, and then d to the fourth power all over 12. And there's our nice simplified answer for number 6. Okay, our next one has a lot of parts going on. So remember, if we can, we want to simplify the top and bottom of a fraction independently. So I think we have some stuff to do, at least a quantity being raised to a power down here that we can deal with first. So because everything down there is being multiplied, we can distribute our exponent over multiplication. Remember back here, we had this property that if everything's held with multiplication, we can distribute the exponent. So in the denominator, that gives us 2 squared. Then we have s squared, that's an s. Then I have t to the 0 also being squared. And the top remains unchanged, 16s to the 6th, t to the 5th. So again, when you have a power raised to a power, remember you multiply your exponents. So down here, we can go ahead and turn 2 squared into 4. S squared squared, multiplying my exponents, we get s to the 4th power. And 0 times 2 would be 0, which hopefully we recognize that that will be equal to 1. Okay, so we still have some more work to do here. Everything up top stays the same so far. But now that I've done 2 squared, I can simplify the 16 and the 4. So if we divide each by 4, we're going to get a 4 and a 1. S to the 6 and s to the 4th, now I can subtract. So s to the 6 minus 4 would be s squared. So positive means it goes up top here. Or remember, it always starts up top. And if I did the same with t, we could do that. T to the 5th minus 0 would just be t to the 5th. So we just get t to the 5th up top. Or again, you can think of as this ends up turning into like a 1. So it's just like times 1 in the bottom, and essentially t to the 0 goes away for us. And because this is just over 1, we don't even need it as a fraction anymore. So 4s squared t to the 5th. Okay, our last example here, m to the 4th, n to the 6th, all over 2n to the 5th. And I could start simplifying inside of here, but if I'm going big brain, if this whole thing is to the 0 power, what's anything to the 0 power? 1, including some big ugly looking quantities. This whole thing is to the 0 power. That means that whole thing is just equal to 1. So sometimes analyzing the problem as a whole before you just start willy-nilly simplifying inside of here, doesn't matter what I simplify that to, it's going to turn into 1 anyway. Okay, that's it for our example, so I'll see you in class where we'll